Good morning, guys. So, thank you for being patient while I made some coffee and grabbed some cereal. I really do appreciate that. It helps me have a lot more energy if I can have those things to help wake up. Today is not a difficult day. All over here, and we can get started. Today we're going to do a few things. I'm going to talk about exam 1. I'm going to do some homework questions. And then we're going to do a somewhat further introduction to trig sub. I know we introduced trig sub just a tiny little bit last time, but today I'm actually going to do some problems for you. I'll show you how that goes. I'll be able to warn you about the particular things that people struggle with there, and just give you a feel for what next week is going to look like. So I'm going to go ahead and talk for a little bit about exam 1, when it's going to happen, how it's going to happen, what it's going to be like. While I do that, I would like you guys to look through the current homework set, homework 4 from section 7.2, and pick out any problems that you would like to see worked today, any that you are having a hard time with. As you find those problems that you would like to see work today, type them into the chat. Just tell me, problem number blank from homework 4 or whatever. So, the test. First things first, the test is going to be 2 weeks from today. So that's Friday, I think the 2nd. And it will be during our normal class time. So instead of coming to class on that day, let me verify that that is the 2nd. Yeah. Instead of coming to class on that day, what you're going to do is you're going to go to Canvas, and you're going to go to quizzes, and then you'll click on exam 1. It's going to be proctored by HonorLog. The questions will be in Canvas. It'll be structured as a Canvas quiz. And so you'll be going into a Canvas assignment to take the test. But we're going to be using the third-party software HonorLog for proctoring. If you haven't used HonorLog before, this is a Chrome extension. And it requires a webcam. If you don't have a webcam, you can go to the library and use one of their computers, although there are only a handful there that have webcams. So if that's your plan, you want to show up early that day. Another option, if you don't want to take the test at one of the computers in the library, we have some loaner laptops. You can actually come up to campus and get a laptop to borrow for a day. And of course, you could use that to take the test. There are going to be 2 assignments in Canvas related to exam 1. Now, 3 if you count the study guide, but 2 directly related to exam 1. The first one is going to say exam 1 questions, take the test here. That's where you're going to go to take the test. The second assignment is going to say, exam 1, submit scans of your work here. That's where you will submit scans of your work after you take the test. So you'll go to the take the test here, exam, work the problems. As you work the problems, you need to write your solutions neatly, one problem per page. So you can do one problem on the first side of your paper, and then problem 2 on the back side of that paper, problem 3 on the first side of the next paper, and so on. Once you finish the test, you'll submit it, you'll get out of that assignment, and then you're going to immediately use probably your phone, but if you have a physical scanner, you can use that also. And I recommend the app Cam Scanner. I'll show you what that looks like here. This thing, Cam Scanner, it's good, it's free, works great. To scan your written work, and then you will submit that under the thing that says submit scans of your work here. The written work is what I'm going to be grading. So as you take the test, you're going to enter only your final answers in the box. And then you'll submit those scans that should have work that lead to that final answer. If you don't submit your final answer in the box during the test, I can't give you any credit. If you don't submit the written work, I can't give you any credit. And if the written work doesn't match the answer you submitted, I can't give you any credit. And one last harsh thing like that, you need to submit the scans within about 5 minutes of finishing the test. Otherwise, I can't trust that that's actually your work that you did during the test. So there's some kind of technological hurdles that you're going to have to hop over to make sure that this goes smoothly, but I promise none of it is hard. The test structure itself, the test will have between 10 and 15 problems. Some of them will be true-false, some of them will be multiple choice, and some of them will be written full-length questions. The true-false problems are worth 2 points each. The multiple choice problems are worth 3 points each, and the free response problems are worth 5 points each. Okay. Are there any questions about how that's going to work? Hey, Hammy boy, how you doing? Handsome as ever, yeah. No, you can't have the cereal. That's Daddy's.
Is the study guide structured similar to the exam?
It's not, no. No, the study guide is just a handful of problems that are going to be posted to a web assignment. I'll post those next Friday, so I always give you a full week to work on the study guide. And then your duty for the study guide is to go into Canvas or go into WebAssign and solve those problems. But as you solve them, you're going to write nice, neat solutions as though they are test problems. And then as soon as you finish that, you're going to submit those nice, neat solutions to the study guide assignment in Canvas. So you'll scan, just like you will the test, you'll scan your written work and submit that in Canvas. The purpose of doing that is so that I can go in there and give you some feedback on that written work before the test. So while study guide 1 in Canvas will not be due until the day of the test, you want to submit it as soon as you can so that I can give you feedback before the test. If you can't submit the whole study guide before that day, then come by office hours, do something to show me your work a little bit so I can tell you, hey, oh, you left this off here, that would be a half point, or you made this mistake here, that would be a whole point, to try and give you an idea for what my standards are like when it comes to grading. I've done my best to communicate them so far through the class, but it's also important, I think, that I interact a little bit with your work. That way you can learn my style, I can learn your style. So let's put this down in writing. And be good. So study guide 1 will be released from WebAssign next Friday. In addition to completing the assignment in WebAssign, you must submit scans of your solutions to the study guide problems in Canvas. It's the work that you submit to Canvas that I grade for the study guide grade. I want to be clear about that. If you do the thing in WebAssign, you answer all the questions in WebAssign, but you don't submit your written work in Canvas, that's still going to be a 0 on the study guide. Study guide should never hurt your grade. I don't go in there and grade them for correctness. I just go in and grade for completeness, but I also write lots of comments and notes that will help you on the exam. So don't forget to do this. Don't forget to submit the study guide in Canvas. You just have to write out your solutions to the WebAssign problems, scan them, and submit them in Canvas. That's where the study guide grade comes from. And you want to do this, you want to submit the written work before the test day so I can give you feedback. All right. The last day you can submit the study guide is the day of the test. All right. So the purpose of the study guide is I will, in WebAssign, select some problems that are about exam difficulty, right? They're about as difficult as the test questions will be. And then you get to practice solving problems like that. In addition to getting you practice, the sooner you get that work submitted, the sooner I can give you feedback, the sooner you can incorporate that into your studying and make use of it on the exam. If you wait until the day of the test to submit your study guide, you'll still get full credit for the study guide, but you're not necessarily going to get anything out of it besides the practice. And really, I want you guys to get more out of it than that. I want you to see how I grade things. I want to see how you're writing things so that we can have a dialogue. If you don't have time to submit the full study guide before the day of the test in time for me to give you feedback, you can always just email me a scan of a question or problem or two so I can see your work and give you some feedback on that. Anything is better than nothing. And the main point of the study guide is to get you some written feedback to let me see your written work before the test, right? In a low pressure environment.
So I have a question.
Yeah.
You said there's like true and false. What is that like centered around? Like, is it stuff from like the textbook or stuff from our notes that we should pay attention to?
It's concept stuff like true, false, the integral of f times g is equal to the integral of f times the integral of g. Right, so my true-false questions tend to be concept-focused and directly related to the material we've been learning. So this is false, right? We have the integration by parts rule that tells us exactly how you can integrate a product. And it is definitely not like this.
Okay.
So things of that nature.
Okay, and then multiple choice is basically solving problems, I assume, because
yeah, an example multiple choice. Which of the following is the result of substituting z equals e to the x in, you know, something like e to the x over 1 plus e to the 2x dx, maybe from 0 to 1, right? And then I would give you 4 integrals to choose from. So my multiple choice questions, things along this line, and my true-false questions will be things along this line. The true-false can be tricky. So a little warning here, a lot of people rush to the free response stuff and kind of don't give the true, false, and multiple choice the love they deserve, usually about half the test comes from the true, false, and multiple choice combined. So true, false, and multiple choice worth about half the test, free response worth about half the test. Both are very important. There is no partial credit on true, false, or multiple choice, of course, but there is lots of partial credit on the free response. Any other questions about the test or the study guide?
Why would you sub EX and not 2X for that example?
Well, because e to the 2x is e to the x squared. And if you tried to sub e to the 2x, you wouldn't have the piece you need for your differential, because if you sub z equals e to the x, dz is e to the x dx. If you sub z equals e to the 2x, then dz would be 2e to the 2x. I do have an e to the x that I can group with the dx over here to make this substitution go through, but I don't have an e to the 2x up here that I can group with dx. So this would give me integral from 1 to e, 1 over 1 plus z squared dz. And if you try the other substitution, it won't work.
And then you realize that's inverse tan, right?
Yeah, from here, this, if you had to solve the problem, which you wouldn't have to for this, right? You'd just have to identify the correct result. From here, it would be an inverse tan of z, yeah. Okay, any other questions on the test or on the study guide? All right, then let's look at some homework problems. Hopefully you guys have a handful that you've picked out. In the chat, I just see 4, 14, and 17. We did number 4, guys. We did number 4 last time, and I think maybe also the time before. Number 4 is the sine squared cos to the 4, right? If I'm remembering correctly. Yeah, we've done this. We've done this a few times. I'll run through number 4 again. That's okay. The other ones we wanted to see were 14, 12, 14, and 17. Okay. So I'm going to go fast through number 4. If you want to see number 4 done slowly, go back and watch Wednesday's video because we did it there. Here I'll do it, but I'm going to do it quickly. So you want to integrate from 0 to pi. I'm going to ignore the constant out front. Sine squared times cos to the 4. Both powers here are even, which means the only attack we have is to repeatedly apply half angle identities. So sine squared I write as 1/2 1 minus cos 2t. And cos squared, or sorry, cos to the 4 is cos squared squared. So that's, I'll write it, why not? Cos squared t squared dt like this, which is the integral from 0 to pi, 1/2 1 minus cos 2t times 1/2 1 plus cos 2t squared dt. The two identities we're using is cos squared theta is 1/2 times 1 plus cos 2 theta, and sine squared theta is 1/2 1 minus cos 2 theta. So if the power of sine and the power of cosine are both even, then this is the only attack we have. We just repeatedly apply these identities until we get to stuff we know how to handle. When I square all of this, I'll get a 1/2 squared times 1 plus cos 2t squared. I can pop the 1/2 squared, which is a 1/4 out front. I can also pop this 1/2 out front, so I'll get a 1/8 out front. Integral 0 to pi, 1 minus cos 2t times 1 plus cos 2t squared. And then from here, I have to FOIL out that second chunk, then distribute the first chunk over it. So I'll get 1/8 integral 0 to pi 1 minus cos 2t. Foiling this, I get 1 plus 2 cos 2t plus cos squared of 2t dt. And then I'll distribute this over this. So when I distribute the 1 here over all of this, I'll just get that back. 1 plus 2 cos 2t plus cos squared 2t. And then I'll distribute the minus cos 2t over all of this. So minus cos 2t times 1 is minus cos 2t. Minus cos 2t times 2 cos 2t is minus 2 cos squared 2t. And then minus cos 2t times cos squared 2t is minus cos cubed 2t. There are like terms I can combine here, the plus 2 cos 2t and this minus cos 2t, the plus cos squared 2t and minus 2 cos squared 2t. So I got 1/8 integral 0 to pi 1 plus cos 2t minus cos squared 2t minus cos cubed 2t dt. And there's two things I'm going to do from this step. I need a modified half angle formula for this, because it's an even power. And I need to split this guy off from this integral and treat him separately because he's an odd power. So the modified half angle identity is cos squared 2t equals 1/2 1 plus cos of 4t. I'm just plugging theta equals 2t in here. So I get cos squared 2t equals 1/2 1 plus cos of 2 times 2t is cos 4t. So I'll have 1 plus cos 2t minus 1/2 times 1 plus cos 4t. There's that modified half angle. And then I peel off the integral of cos cubed. Questions up to here? How do I do the integral of cos cubed? Does anybody remember that part from Wednesday?
Could you set aside a copy of
Yeah.
cos cubed and then use the identity, the Pythagorean identity?
Good. I set aside one copy of the cosine of 2t, and I'm doing that thinking about substituting for sine. So I need to rewrite this in terms of sine. And the other stuff here, I can distribute this 1/2, and that'll give me a 1 minus 1/2 is a positive 1/2, the plus cos 2t coming for the ride, and then I'll have minus 1/2 cos 4t. Like so. So this 1/2 right here, take a second and follow me on this. This 1/2 right here is this 1 minus the 1/2 I get when I distribute to this. So this piece is ready to go. I know how to integrate everything there. This piece, I need to use a trig identity and then make a little substitution. So my antiderivative here is 1/2 t plus sine 2t over 2 minus integral of cos 4t would be sine 4t over 4, but I've got another 1/2 here, so it's going to be sine 4t over 8, evaluated from 0 to pi, minus 1/8 integral 0 to pi, 1 minus sine squared of 2t, that's the first Pythagorean identity, times the cosine of 2t dt. So cos squared of anything is 1 minus sine squared of that thing. That's the first Pythagorean identity. And then here in this guy, I'm going to make the substitution z equals sine of 2t. So that dz is 2 cos 2t dt. And something interesting happens when we change the bounds. My old bounds were 0 to pi. When t is equal to 0, z is equal to the sine of 2 times 0, which is 0. And when t is equal to pi, z is equal to the sine of 2 pi, which is also 0. That's funny. On the other hand, over here, when I evaluate, if I plug in the upper bound of pi, I'll get 1/2 times pi. Sine of 2 pi is 0, sine of 4 pi is 0. So that's all I get from my upper bound. And when I plug in my lower bound 0, this is 0, 1/2 times 0. Sine of 2 times 0 is the sine of 0, that's 0. Sine of 4 times 0 is sine of 0, that's 0. And then this integral here is going to become minus 1/8 integral 0 to 0, 1 minus z squared times 1/2 dz, which is a funny looking thing. You may remember from Calc 1, if you don't, let me remind you. The integral from a to a of any function, that's always 0. So this piece right here is 0. We don't even need to do the integral. So the whole problem just comes down to this piece, which is pi over 16. This piece right here is 0 because of this. Okay, so I know that was a little bit quick, but this is a second or third time through this problem. I know this problem is tricky, so it's okay that we're spending a little bit of extra time on it. I want to make sure we're really comfy. So are there any questions about any of these steps? Don't be shy. If you're wondering something, probably a few other people are too. Everybody feeling good? Really what we have to do is keep in mind those strategies, right? So if the powers of sine and cosine are both even, then you just repeatedly apply these identities. And there's a meaningful amount of algebra here, but it is just the application of half angle identities. We do those twice, right? Once in this line, and then again in this line, right? Down here, placing cos squared by 1 plus cos 2 times his inside. It's a little bit sneaky to peel off the cos cubed, but it's also totally reasonable because here the power is odd. He gets his own special treatment because he's a different shape than the other guys. And again, you could use a geometric argument to say that this integral is 0 rather than going through this process. But I think this process is the most natural thing for a Calc 2 student. But I don't think most of us know what the graph of cos cubed 2t looks like off the top of our head. Last call for questions on this. Okay, moving on then. So 12, 14, and 17, right? Oh, homework 3, number 12. Yeah, okay, let's go back to homework 3 for a second. Oh, this is a good one. So here we're integrating from 1 to the square root of 3, the inverse tangent of 1 over x dx. So I'm going to run IBP, and I use
Yeah, I see the
LIPET.
screen.
Oh, sorry, thank you. So here I'm going to run IBP and use LIPET to choose u and dv. U being the, I follow down my LIPET rule. I don't have any logs, but I do have this inverse function. So I'll pick u to be the inverse tangent of 1 over x. And dv then is just dx. You may need to remind yourself how to differentiate arctan. So I'll say recall. The inverse tangent of some stuff, and I'll say that stuff is f of x, will differentiate to 1 over 1 plus f of x squared times f primed of x. It's the chain rule. Damn, my pen's somewhere here. So the inverse tangent of 1 over x will differentiate to 1 over 1 plus 1 over x squared times the derivative of 1 over x, which is 1 over 1 plus 1 over x squared times negative 1 over x squared. Because the derivative of 1 over x is negative 1 over x squared. And you can clean this up quite a bit. This is 1 over 1 plus 1 over x squared times negative 1 over x squared. And if you multiply those fractions straight across, you'll get negative 1 over x squared plus 1. The x squared times 1 here gives this x squared. The x squared times 1 over x squared gives this 1. So du is negative 1 over x squared plus 1 dx. and v is just x. Right, so some side work. As the result, this integral, the integral from 1 to √3 of the inverse tangent of 1 over x dx is equal to u times v. I'll write the x out front because it looks better that way. Evaluated from 1 to √3 minus the integral from 1 to √3 of v times du. That's x times -1 over x squared plus 1 dx. So we should evaluate this piece between 1 and √3, and we should also be thinking about how to solve this integral. In my next line, I'll do the evaluation and I'll pop this negative out, making this minus a plus. When I plug in √3, I get √3 times the inverse tangent of 1 over √3. And you need to know what the inverse tangent of 1 over √3 is. Minus 1 times the inverse tangent of 1. And you need to know what the inverse tangent of 1 is. And then I'll have plus integral 1 to the square root of 3. All right, this says 1 over x squared plus 1 times x dx, because I'm thinking about making a substitution there. All right, who can help me out? What is the inverse tangent of 1 over the square root of 3? That is the angle between -π/2 and π/2, so that the tangent of that angle is 1 over √3. Good, this is π/6. This is √3 times π/6 minus, what is the inverse tangent of 1?
π/4.
Good. Now in this integral, I want to make a substitution. What do I want to substitute for here? I want to let z be, what would make a good substitution in this integral? Yeah, the denominator there, x squared plus 1. Then dz is going to be 2x dx, and I also need to change my bounds. When x is equal to 1, z is equal to 1 squared plus 1, that's 2. If you don't change your bounds on your definite integrals, I will be taking points off. When x is equal to the square root of 3, z will be equal to the square root of 3 squared plus 1, which is 3 plus 1 is 4. So my new integral here, I'll have a 1/2 coming from this differential. X dx is 1/2 dz. Integral 2 to 4, 1 over z dz. And this piece will become a natural log. So I get √3 π/6 minus π/4 plus 1/2 times the natural log of the absolute value of z evaluated between 2 and 4 which is root 3 pi over 6 minus pi over 4 plus 1/2 times the natural log of 4 minus the natural log of 2. And if you want to, you can combine the natural log of 4 and the natural log of 2 using the rule ln b minus ln a is the ln of b over a. So this would be root 3 pi over 6 minus pi over 4 plus 1/2 times the natural log of 4 over 2, which is 2. So this is a good problem. I think the only tricky piece here is calculating du. You need to be really comfy with the chain rule. And then maybe changing those bounds is a little bit tricky also. I'm sorry, not changing the bounds, but evaluating this piece. I'll tell you that where we're going, section 7.3, there is a lot of trig, not just regular trig, but inverse trig. And so you need to really know your unit circle. You need to really know the definitions of the inverse trig functions. You need to know the associated domain restrictions. All of those things are completely necessary. Questions about any of these steps?
How'd you get the natural log of 2 at the end?
So I used this rule for logarithms to simplify log 4 minus log 2. So
Okay, yeah.
log 4 minus the log of 2 is equal to the log of 4 over 2. And 4 over 2 is 2.
Okay.
It's a good question. Any other questions here? It would be okay if you left it like this, right? I wouldn't take off any points. This is correct and it's finished. If you wanted to go further from here, you could. You could bring that 1/2 inside as a power and write this as plus ln square root of 2 if you wanted. But I don't see any need to do that. All right, then let's get to those problems. What do we want? Homework 4, number 17 and 14, right? Let's look at 14, and we'll do 17. No, that's the old one. That's the new one. So 14 is fun. I think so. You guys are the first people to ask me about this. I'm excited to take a look at it. It's been a while. We want to integrate 5 sine phi over cos cubed phi. So that symbol there is the Greek letter phi or phi, some people pronounce it. I can pop the 5 out, of course. I get this. And then the trick here is going to be rewriting as like secants and tangents, right? Because the cosine is downstairs, not upstairs. This is not a sine cos integral. It's actually a secant tangent integral. You just have to rewrite it. So I'll write it like this. 1 over cos squared phi times sine phi over cos phi d phi. Because downstairs I had a cos cubed. I can split that up like this. And then this piece is what? What is 1 over cosine?
Secant.
Yeah, that's the definition of secant. So 1 over cos squared is secant squared of phi. And sine over cosine, of course, is tangent. Whew. So I got a little bit silly making all these loopy things. Yeah, so I get secant squared phi times tan phi d phi. How do we do this integral? Is this an easy integral or a hard integral?
It'd be easy because secant squared is the derivative of tangent.
Mm-hmm. So that tells us we should do what?
Substitute with tangent for z
Good.
and secant squared d phi for dz.
Perfect. So let z be the tangent of phi. dz is then secant squared phi d phi. It's an indefinite integral, so I don't have to change any bounds. And I get 5 integral secant squared phi d phi, that's my dz. And z is tan phi, so I just get z dz. So my antiderivative step here, I'll have 5 times z squared over 2 plus a constant, which is 5 times tan squared phi over 2 plus a constant. And you could write that as 5 halves tan squared or 5 tan squared over 2, however you want. Not too bad. We get to enhance our vocabulary with a new Greek letter. That's always fun. And we get a little bit of practice rewriting ratios of sine and cosine as secants and tangents. I know that trigonometry here at Santa Fe is weak. I wish it wasn't that way, but it is. So you may need to practice this stuff. I want to remind you that if you go into our Canvas modules, I've got lots of trig stuff here, right? This page on algebra and trig review is very good. The explicit trig stuff is very good. And down here, right, you've got inverse trig functions, solving trig equations, trig formulas, graphs of trig functions, evaluating trig functions, all very important. So if you don't remember this stuff, give it some time. If you don't remember how to do this stuff, this is exactly the stuff we're using right now, yeah? Cos squared is 1/2 1 plus cos 2x. Sine 2t is 2 sine t cos t. All that stuff is right there. So please take the time to make sure your skills with trig are where they need to be, because especially next week, not only is it going to be important, it's going to be important like in the middle of the problem as a step rather than as the whole thing. So it needs to come fast. It needs to be fluid. The last one I saw anybody requesting was number 17. This is a fun problem too. I'm going to integrate 3x sine squared x squared dx. This is homework 417. Has anybody attempted this one yet? Any ideas what we could try?
I haven't attempted it yet. Would you start by combining 3x and x squared?
Well, the x squared is trapped inside the sine.
Oh, I missed that.
So I can't combine those. The x squared is inside the sine function. IBP is an option. It looks kind of like an IBP problem, doesn't it? Because I've got a polynomial times a trig function. But if you pick u to be this, and then dv to be this, then the dv to v step would require you integrating sine squared of x squared. That's a hard integral. That's a very hard integral. So a substitution is the right way to begin. And then maybe some IVP, but I don't think you'll need IVP after you substitute. So I'll pop the 3 out and write this as sine squared of x squared times x dx. My substitution people, what substitution are we thinking? Oh, I see it right there, z sub for x squared, good. So z equals x squared, dz is 2x dx. So I'll get a 1/2 out because x dx is not dz, it's 1/2 of dz. So I'll get 3/2 integral sine squared of z dz. And then it's reasonable to think you would need IBP afterwards, but here we really don't. Right? All the polynomial stuff is gone, so there's no need for any integration by parts. This is now a straight up trig integral. So how do I integrate sine squared? Think of,
Half angle formula?
yeah, good, half angle, yep. So sine squared z is 1/2 times 1 minus cos 2z. So this 3/2 will become a 3/4 because there's a 1/2 coming from the identity. And then I'll have 1 minus the cos of 2z. So here I'm using the half angle identity for the sine function. And now everything is easy. That's 3/4 integral of 1 dz is z. Integral of cos 2z is sine 2z over 2. And then finally, because it's an indefinite integral, I have to go back to my original variable. I'll also distribute the 3/4. So I'll get 3/4 times z, which is 3/4 times x squared, minus, I've got 3/4 and then a 1/2 here, so that's 3/8 times the sine of 2z, that's the sine of 2x squared, plus a constant. It's a neat problem.
So I have a question.
Yeah.
Do you only use the half angle identities when dealing with problems that like have sine squared alone, or?
So we use half angle identities when you're looking at any sine cosine integral where the powers are both even. So if you've got integral sine to some power times cos to some other power, if both m and n are even, then we use the half angles. So not just if you have sine squared or cos squared alone, like think of problem 4, the one we did at the start, that had sine squared times cos to the 4. And we beat both of those down with half angle identities. So if you have a sine cos integral and both of the powers are even, then you use the half angles. If you just have like sine squared and there is no cosine, then really there is a cosine, it's just that the power is 0, and 0 is an even number. So those fall in as a special case of this rule. Does that answer the question clearly?
Yes.
Okay, cool. Yeah, so if you're looking at an integral that is powers of sine times powers of cosine, and you don't see any odd powers, that's when we use half angles. Okay.
Can you use the half angle thing for like tangent?
You don't need to. Right, so the secant tangent integrals, remember the way those break down. If the power of secant is even, then you substitute for tangent. If the power of tangent is odd, then you substitute for secant. And in both of those cases, the only identities you need are the Pythagorean identities. If you're not in that case, then the power of tangent is even and the power of secant is odd. And in that instance, you use integration by parts. So there is no place where half angles for tangent or secant are helpful, unfortunately. The half angle identities for tangent and secant are not as nice as the half angle identities for sine and cosine. They just don't look the same. So there isn't a situation where they're helpful for integrals. But that's a fair question. So we just have to remember those cases, right? If they're not sticking in your brain just yet, you might want to go back to Monday's video for the sine cosines and Wednesday's video for the secant tangents, and make sure you have written clearly in your notes the cases for each. Each fall into 3 cases. The sine cosine integrals, either the power of sine is odd, the power of cosine is odd, or both powers are even. If the power of sine is odd, you're going to try substituting for cosine. If the power of cosine is odd, you're going to try substituting for sine. And if both powers are even, then you're going to beat the things to death with the half angle formulas. The secant tangent integrals break down into the 3 cases. The power of secant is even, the power of tangent is odd, or neither of those are true, meaning the power of secant is odd and the power of tangent is even. If the power of secant is even, you're going to substitute for tangent. That's the first case. If the power of tangent is odd, you're going to try substituting for secant. And if neither of those are true, if you're in the bad case, where the power of secant is odd and the power of tangent is even, then you're going to use integration by parts and make that a looping integral. I'll remind you, the textbook breaks these down very well. And if you need to review those results, you can find them in section 7.2 here. You should always read the text. But they do a nice job, not just of giving examples, but giving you those 3 cases. And then here they break it down into 2 cases and then say everything else. And everything else here is where the power of tangent is even, the power of secant is odd. You'll use integration by parts. Okay. So how are we doing for time? 10:38. That's about right. I want to talk a little bit about what we're going to do next week. The motivation here is that the square root of a plus or minus b, let's say a squared plus or minus b squared, cannot be simplified as a plus or minus b. This shit literally never works. So if we want to integrate something like 1 minus x squared, I cannot begin by saying that that is 1 minus x. So what the hell can I do? The Pythagorean identities, like sine squared theta plus cos squared theta equals 1, give us a hint as to how we can handle stuff like that. This implies, for example, that cos squared theta let me write it. Yeah, I'll write it like this. This implies that 1 minus sine squared theta is equal to cos squared theta, right? Which means that the square root of 1 minus sine squared theta is the square root of cos squared theta, which is just cos theta. Similarly, if I take the second Pythagorean identity, this implies that the square root of tan squared theta plus 1 is the square root of secant squared theta, which is just secant theta. Why is this nice? So when we see something here in our integral, we want to substitute if I see a square root of 1 minus x squared in my integral, I want to substitute x equals sine theta, because then the square root of 1 minus x squared would be the square root of 1 minus sine squared theta would be the square root of cos squared theta, which is just cos theta. In other words, if you have something like this floating around in your integral and you make this substitution, it will become really, really nice. In particular, the magic happens right here. 1 minus x squared is 1 minus sine squared. 1 minus sine squared is cos squared. So the subtraction goes away. And we know square roots hate addition and subtraction. That's the point of the thing at the start here. So by getting rid of the addition or subtraction underneath the square root, I get it to something I can manage. Similarly, if I had something like square root of x squared plus 1, then I would want to sub x equals tan theta, because then the square root of x squared plus 1 would become the square root of tan squared theta plus 1, which would be the square root of secant squared theta, which is just secant theta. So you can get rid of these weird square root expressions by substituting in the appropriate trig function. Notice that x equals sine theta, for instance, is kind of backwards from a u sub, in the sense that my old variable is a function of my new variable, which is theta. Usually when we make a substitution, our new variable is given as a function of my old variable, like z equals x squared. Here, my old variable is given as a function of my new variable. So the roles are kind of swapped. This changes how we handle the differential. It actually makes life easier. So normally when I make a substitution, a z sub or a u sub, I have to have the appropriate piece floating around in my integral to soak up the du or the dz. Like if I want to substitute for x squared, I need an x dx already in my integral. Here, I'll show you how it goes. It's actually much simpler. I'd be willing to bet that some people remember this integral. It is a Calc 1 integral that you're supposed to more or less memorize. But also I know a lot of people forget it. My integrand there, 1 over the square root of 1 minus x squared, this is the derivative of the inverse sine function. So the integral of this is inverse sine. But if you happen to forget that, you can use the rules that I just discussed. I have a square root of 1 minus x squared, which should make me want to substitute x equals sine theta. I'm making a substitution, so I still need to handle the differential. The difference is here, when I calculate the differential, the left-hand side, I just have dx. Over here, I'll have cos theta d theta. So rather than trying to find the differential in my original integral and replace it by some related piece, I'm just going to plug in for dx. dx is cos theta d theta. So it's actually much simpler than u sub in that sense. So now everywhere there's an x, I'm going to write sine theta. So this will be the square root of 1 minus sine theta squared times dx. Well, dx is cos theta d theta. Just like in u subs or in any other substitution, if there were bounds, I would have to change them. And I can't proceed until everything is in terms of my new variable. In particular, dx has to be replaced by cos theta d theta before you can do anything else. But now this is remarkably nice. That's 1 over the square root of 1 minus sine squared theta, right? Sine of theta all squared is sine squared theta, times cos theta d theta. And downstairs in that square root, 1 minus sine squared is cos squared. That's the first Pythagorean identity. So this is so nice. 1 over cos squared, or 1 over the square root of cos squared is 1 over cos. And then I've got my cos up here from the differential, and they will cancel. And I just get the integral of 1 d theta. Which is theta plus c. The last thing I need to do is go back to my original variable. It's an indefinite integral, so I got to go back to the original variable, which was x. And if you take my substitution here and try to solve it for theta, x is equal to sine theta implies that the inverse sine of x is equal to theta. That's what sine inverse means. So theta plus c is inverse sine of x plus c. And like I said, if you knew this integral, if you remember this, it's that. This is trig sub. This is a very simple example. And next week, we're going to explore a lot more subtleties, things that can happen with this. But this is the basics, okay? So this is where I'm going to leave us for today. I do have my normal Friday office hour this afternoon. If you want to come by and talk problems from any homework set, we can do that. Please try to finish up the 7.2 homework 4, as soon as you can. Definitely needs to be done by Monday so you can focus your attention on trig sub. Next week, we're going to talk about trig sub and partial fractions. So the layout, the schedule, the plan. Next Monday is going to be all trig sub. And we'll get through the whole section. It's a quick section, but I know that it's not easy stuff, especially if you forget some of your inverse trig. So it's easy to teach, but it's going to be a difficult homework, I think, for most of you. So then Wednesday, we'll do a little bit more trig sub at the start of class, but then most of Wednesday is going to be spent on partial fractions, section 7.4. And then Friday is going to be all partial fractions, 7.4, and we'll finish that section on that day. I will release the study guide on next Friday. And so you'll have all of next week to work on the study guide. Monday of next week, I'm going to be doing some new material, right? It'll be stuff that's not on exam 1. So the cutoff for the material that will be on exam 1 is next Friday. Monday of the week after, I will introduce you to the material we'll be doing after exam 1. Wednesday, we will review for the test. And then Friday, instead of having class, you will have the test itself. This is also the day that your study guide is due. It must be turned in by Friday. Hopefully you'll turn it in sooner than that. It's only going to be like 10 problems long. And I want you to turn it in as soon as you can so I can provide you some written feedback. I think that's very important before the test. But that's the layout, okay? So next Monday, trig sub. Next Wednesday, little trig sub, mostly partial fractions. Next Friday, all partial fractions. The Monday after that is going to be stuff that's not relevant to exam 1, but will be relevant to exam 2, just so we don't lose time. And then next Wednesday will be the review for the test. Friday will be the test itself, okay? Any questions for me before we part ways for the day? Alrighty then, I hope you guys have a lovely rest of your afternoon. Feel free to come say hi in office hours. We can talk about problems, whatever. Otherwise, I will see everybody bright and early on Monday. Have a lovely afternoon.